In this example, we're going to work through calculations for a vapor compression refrigeration cycle. And to make it easier to follow, we've put the data that we're going to need into a table to avoid having to search through tables to understand what's happening. And best way to look at the information is to look at a pressure enthalpy diagram. That tends to be most useful for refrigeration. So we're going to put the data given in the problem statement into this diagram where the phase envelope looks something like this. And now the problem states that the upper pressure corresponds to temperature 45 degrees C. It says we reach saturated liquid here. The course going through the throttle is at constant enthalpy, and then the lower temperature is minus 10 degrees, so this is minus 10 degrees C, and it says this yields saturated vapor. And so then when we go through the compression, so let me extend this line a little bit. When we go through the compression, if we do it reversibly and adiabatically, then we see an increase in enthalpy because we're putting energy into the system. Well, this says efficiency is 80%, which means we're somewhere more to the right of this. We have to put more energy in to get the same pressure. So now we're going to do the calculations by first looking at a reversible compressor in order to determine the work for the irreversible compressor. And let me label these points 1, and I'll call this point 2 reversible, and then the irreversible, let's call it 2 prime, 3, and 4. So first calculation then is the compressor. For the reversible case, S1 would equal S2. And S1, this is saturated vapor, minus 10 degrees C. So saturated vapor minus 10 degrees C. Here's the entropy. So S1, which is equal to S2, is 1.73 kilojoules per kilogram degrees Kelvin. So S2 now has to have that same entropy. Of course, S2 is at a higher pressure. Well, the pressure is 12 bar because we can see here the 12 bar, that's for the case where we have liquid and vapor. So 45 degrees is the saturation temperature. We're at a higher temperature, but the same pressure. So here is the value corresponding to our condition, S2. So this means we know the enthalpy at 2, and that's 430 kilojoules per kilogram. Well, enthalpy at 1, the saturated vapor minus 10 degrees is 393. And so we can calculate delta H then for the reversible compressor, and that's H2 minus H1, so that's 430 minus 393, and that's 37 kilojoules per kilogram. So remember, this is reversible. The delta H is equal to the work. So the work reversible is delta H reversible because it's adiabatic. So we know the work we have to add for the reversible case. Well, what we're interested in is the irreversible case. So the work for the irreversible case, when the efficiency is 0.8, the work has to be more. So it's the reversible work over 0.8, 37 over 0.8, 40. Let's keep the significant figures for now. The work is larger. This is the irreversible work. Well, the irreversible work then is the enthalpy change for the irreversible. So that's H2 prime minus H1, which means H2 prime is H1 plus 46.25. Well, we already used H1 already, right? H1, 393 kilojoules per kilogram. 393 plus 46.25. So 439 kilojoules per kilogram is the enthalpy at 2. Now calculate the heat. We need enthalpy at 3. Enthalpy at 3 is saturated liquid, 45 degrees C. So 45 degrees saturated liquid. Here's the enthalpy. So the change as we condense this fluid, we condense it by removing energy. So heat that we remove, and that's at the high temperature, would be H3 minus H2 prime. Saw that 265 is the saturated liquid, and we just calculated that 439 was the entering into that condenser. So QH then, minus 174 kilojoules per kilogram. Well, this is one of the values we wanted to calculate for the problem statement. So finished one part, and we're going to now calculate QC. So, keeping in mind the diagram, we're going to need H4, but H4 is the same as H3 because we're going through a throttle. So H4 then is our 265. So this is also 265 kilojoules per kilogram. And H1, we've already calculated 393. So that means if we want to calculate QC, this is the cooling, how much energy we remove from our low temperature refrigeration section of a refrigerator, put in at minus 10 degrees into this cycle. That's H1 minus H4, the final minus initial, and H1 is 393, H4 265. So this is 128, and it's positive because we're adding energy into our cycle. And this is QC. Remember, this is QH. So last thing we need to calculate is the coefficient of performance. Coefficient of performance is QC over W. 128. Remember, this is irreversible work. 46.25, 2.77. So coefficient of performance is 2.8.